A ball is launched from the top of a 50-foot tall building, reaching a maximum height of 100 feet above the ground before it begins falling. The ball takes 3.02 seconds to reach the ground after being launched. We will let the variable t represent the number of seconds since the ball was launched. The function k of t equals -32 times t squared plus 80 times t determines the ball's height in feet above the top of the building in terms of the number of seconds t since the ball was launched. So k of t represents the ball's height in feet above the top of the building t seconds after the ball was launched. When the ball is launched, t equals 0. When the ball hits the ground, t equals 3.02. As the ball travels, the time since the ball was launched increases continuously from t equals 0 to t equals 3.02. Therefore, t assumes all values between 0 and 3.02, including 0 and 3.02. Since t is the input variable of the function k, and we are only concerned with values of t between 0 and 3.02, we say that the domain of k is the values between 0 and 3.02, including 0 and 3.02. We can represent this set of values using interval notation as the closed interval from 0 to 3.02, where the square brackets indicate that both 0 and 3.02 are included in the set of values. Therefore, we say that the domain of k is the closed interval from 0 to 3.02. In general, the domain of a function is the set of all values that the input variable of the function can assume. In this course, we will generally use interval notation to represent the domain of a function. Now, let's look at what values k of t, the ball's height in feet above the top of the building, can assume. When the ball is launched, k of t equals 0, since the ball is 0 feet above the top of the building. As the ball travels upward, the value of k of t increases from 0 to 50, since k of t equals 50 when the ball reaches a maximum height of 100 feet above the ground, which is 50 feet above the top of the building. Then, as the ball falls to the ground, the value of k of t decreases from 50 to -50, since when the ball hits the ground, it is 50 feet below the top of the building, which is -50 feet above the top of the building. So, as the ball travels, the ball's height in feet above the top of the building, k of t, first increases from 0 to 50, and then decreases from 50 to -50. Therefore, k of t assumes all values between -50 and 50, including -50 and 50. And so we say that the range of k is the set of values between -50 and 50, including -50 and 50. This is represented in interval form as the closed interval from -50 to 50. In general, the range of a function is the set of all values the output of the function can assume. In this course, we will generally represent the range of a function using interval notation. The expression -32 times t squared plus 80 times t represents the output of the function in terms of the input, and we call this expression the rule of the function k. It tells us how to determine the output value of k provided a value for the input. In general, the rule of a function assigns to each value in the domain one value from the range. Therefore, given a specific input value, the rule determines exactly one corresponding output value, and hence the rule tells us how the input and the output of the function vary together. The rule of a function can be in the form of an expression, a table of values, a graph, or sometimes even just a worded description of how two quantities are related. In general, a function is comprised of three parts. These parts are a domain, which is the set of all values the input variable can assume, a range, which is the set of all values the output of the function can assume, and a rule, which assigns to each value in the domain exactly one value in the range, so that given a specific input value, the rule determines exactly one corresponding output value. In the ball launching context, we used function notation to define the function k. We call k the name of the function. We call t the input variable of the function k, which represents the number of seconds since the ball was launched. We call k of t the output of k, and this represents the ball's height in feet above the top of the building t seconds after the ball was launched. For example, the expression k of 1.53 represents the ball's height in feet above the top of the building 1.53 seconds after the ball was launched. The expression -32 times t squared plus 80 times t represents the output of k in terms of the input variable t, and we call this expression the rule of k. Now, let's consider two scenarios relative to the ball launching context. First, suppose that we know that 1.5 seconds have elapsed since the ball was launched, and we want to know the ball's height above the top of the building. We can evaluate k at t equals 1.5 to determine the numerical value of k of 1.5, which represents the ball's height in feet above the top of the building 1.5 seconds after the ball was launched. If we evaluate k at t equals 1.5, we see that k of 1.5 equals 48, and hence the ball is 48 feet above the top of the building 1.5 seconds after it was launched. Now, suppose we want to know how long it takes for the ball to reach its maximum height after being launched. In this case, we know that k of t equals 50, and we want to know the value of t. We can solve k of t equals 50 for t to determine this value of t, but doing so involves solving the equation -32 times t squared plus 80 times t equals 50 for t, which might be a little more work than we need to do. If we graph the function k, we can use the graph to approximate the solution to k of t equals 50. Since the vertical axis represents values of the ball's height in feet above the top of the building, we look for all points on the graph of k with a vertical component of 50. There is only one such point, and the horizontal component of this point is about 1.25, and hence the point 1.25, 50, is on the graph of k. Since the horizontal axis represents value of t, the number of seconds since the ball was launched, the point 1.25, 50, on the graph of k represents that 1.25 seconds after the ball was launched, the ball is 50 feet above the top of the building. Therefore, t equals 1.25 is the solution to the equation k of t equals 50, and we say that 1.25 seconds after the ball was launched, the ball reaches a maximum height of 50 feet above the top of the building. In general, evaluating a function at a given input value is the process of determining the output value of the function at that given input value. And solving an equation like f of x equals a for x is the process of determining all the input values of f that result in an output value of a.